Hello, in this video we're going to talk about double integrals over rectangles. So before we do this, I'd like to take a trip back to Calculus 1, where we approximate the area under the curve by Riemann sums. So let's take a look at this graph. We have a function y equals f of x, and suppose we wanted to approximate the area under the curve from a to b. Well, we let n equal the number of rectangles, and delta x equals b minus a over n. And delta x represents the width of each rectangle. So let's take a look at one of these rectangles. These rectangles look like the following. So as we said, the width of the rectangle is delta x. The left-hand endpoint of a given rectangle would be x sub I, and the right-hand endpoint would be x sub I plus 1. And depending on whether we're doing a left Riemann sum or a right Riemann sum or maybe a midpoint, the height of our rectangle would be f of x sub I. In other words, the area of this rectangle would be f of x sub I delta x. So if we wanted the total area under this curve, we could approximate that by the sum of all the individual areas. Right? We could do the area of the first rectangle, the second rectangle, etc. up through the nth rectangle. The way that we would write that would be like this. We would say the area is approximated by the area of the first rectangle plus the area of the second rectangle plus dot 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 all the way up through the nth rectangle. And each of those rectangles areas are found by height times width. And there's a shorter way of writing this. It's using the sigma notation. And so we would say I equals 1 to n. So that sigma means to take a sum. And what we're going to sum up are the areas f of x sub I times delta x. And so we say area is approximated by that sum. That equals the integral. So notice that that integral also looks like an S or a sigma or a big summation. It looks like the definite integral from a to b of the heights, which are the f of x's, times the widths, which instead of delta x we call dx. We're going to use a similar strategy here in Calc 3. So in Calculus 3, we want to find the volume under a surface. So let me draw a surface here, and the surface I'm going to draw for you looks like z equals negative x squared plus y squared plus 16. Okay, so the maximum value of this function will be 16, and when we intersect here with the xy plane, it's going to look like a circle, and kind of looks like a dome shape surface if we come down like that. And we might be interested in finding the volume over some little patch, okay? And this little patch here is going to be called R. So I'm going to let R be the region defined by 0 less than or equal to x less than or equal to 2 and y between 0 and 2. And so a nicer way of writing that might be to say closed interval 0 to 2 by closed interval 0 to 2. And this tells you about the x and this tells you about the y. Okay, so I want to find the volume under the surface and over this region R. And so if we try to figure out what that would look like, the solid looks something like the following. Let's take this. Okay, so this solid has a rectangular base and then it has a curvy top on it. It's almost like a piece of cheese that somebody bit the top off of, right? So it's rectangular on one end, but the other end has kind of this curvy nature to it, defined by this surface z equals negative x squared plus y squared plus 16. All right, so the question is, how can we figure out the volume of this oddly shaped 3D figure? And the strategy that we're going to use is very much like what we did back in Calculus 1. We're going to discretize our space. So we'll take and we'll make very tiny little rectangular prisms. And so we'll have a bunch of different rectangular prisms. And an individual rectangular prism, if we look at that, it will have this rectangular base, and up we go. We'll have to figure out some height. Okay, and to figure that out on the base here, this will be some area. We'll have to figure out what that is, and then the height, we'll pick some point that lives in that little rectangle. We'll call that point x star y star, and then we'll apply the function to it, and that will give us the height. And so we'll be in a good position to figure out the volume, whereby the volume equals this area of the base times the height. Okay, so let's make this more precise. Here's our game plan, and then we'll get to some examples. The game plan is that we're going to take a big sum, and the sum is going to be from I equals 1 up to m. We'll also need to sum up the number of rectangles going in the other dimension, right? We've got x and y directions to take account for, and then we'll be taking these x star y star points that live in the ijth rectangle times delta a. And when we do the limit, as n and m go to infinity, this is going to give us the double integral over some region R of f of xy dA. Okay, so definition: if f of xy is greater than or equal to 0, and what we mean by this is that our function lives up here above the xy plane. Okay, so it's not down below, but it lives up above the xy plane. So if f of xy is greater than or equal to 0, then the volume V of the solid that lies above the rectangle R and below the surface Z equals f of xy is V equals the double integral over R of f of xy dA.